you. If I can get the pointer, that would be nice, and my slides would be great. So what I will be trying to do in these 15 minutes is to give you a little bit of a flavor what the astronomy is going in on that themes. I mean, it's a very vast topic. Thank you, Tim. Very vast topic, and it's really not enough to give you everything. So I think Madhu will, after me, give you a bit more specific element. But I want to give you a teaser, essentially, what's going on. And actually, there is something very profound here. I think the game has changed the way we see that. Certainly, from the 60s or 70s perspective, that was mentioned before. Okay, so I would like to start with a couple of facts, something very simple. The first one is this kind of aesthetic conjecture that, as a physicist, we all have in mind. It's not shared by everybody, and actually it was proposed, the way it was phrased by Christian de Duve, that the fact you have life in the universe is not something which is magical, which is random. It's written in the fabric of the universe. So as a physicist, something that resonates a lot, because when you think about the whole story about the universe, in a sense, the kind of moment when you create time, space, and baryon, essentially hydrogen, or I mean ionized hydrogen, and then neutrinos and photons, there's not much at that moment. Well, actually, the star machinery is creating all these atoms that is on body right now, and even this atmospheric, these atoms and this complexity of the atom you get in the free space, even if it makes water, I was mentioning before, it doesn't go very far. To really do complex chemistry, you need pressure, you need solvent, and then you need to have this on the planet. So all this, in a way, was encrypted in the fabric of the universe from the very beginning. So the law of physics enable life, in a way, on Earth. So as a physicist, there's no limit to that. There should be life everywhere. That's really this kind of a way of thinking through this. Now, we have to admit that as of today, we have not a single evidence of life accepted on this planet. Now, I would like to quote Carl Sagan here that, I mean, set the scenery in the right way. He said the fact we don't have evidence doesn't mean that there's evidence of absence. And that's why, essentially, we can say anything we want, which is nice. So it gives rise to sci-fi. You can think about that. You can invent anything you want. This is cool, because that's a fact we're having. So now, from this perspective, there is two boundary conditions we are playing with, and it has been mentioned many times here during these discussions. The first one we have is, on one side, we know that life on Earth is a singular replica shaped by evolutions. So we have life here, and that's a starting point, and that's still the only model we have in mind, which is fascinating because essentially some even people mention this life with an upper letter. It's only one life. There's nothing else. And that's really what is giving you one angle. Now, this angle is very misleading because when you look at that, you don't really feel that, because if you look at the tree of life, the way you express it through time, we have this amazing diversity right now we see, but still, we have to remember that it's just replications, something that was done much early on. So despite the fact you have this immense diversity, if you look where we are, we're just in the very far corner to the right, so we can see significant seen from the perspective of the astronomers here. So it's still a huge diversity here, and we can even push a little bit further. I mean, you see the magic, the major impact on some feature that define all this boundary condition between the era in the study of the Earth. There's just some gaps here, there. I mean, the massive extinctions, they're not really relevant globally, and practically the common life on Earth is completely free of any impact, which is the bacteria, which actually are old ancestor here. So we have this perspective of this unique life just replicating based on a single model that creates this immense diversity right now. So the challenge here is, what can we say about the beginning? What makes this beginning so special? What are the conditions for the beginning? So that gives you one part of the story here. Now you have to go on the other side and to look at the extreme side. And the extreme has completely changed. So we have to admit that right now there's plenty of planets. And it's pretty clear that we can expect that a lot of them will be potential life hosts. While you don't really know what it means, because you can think about Mars being an ancient life host, and maybe Venus as well in the past. So it's not very clear, but clearly there's understanding that number of planets we're dealing with, and I will go a little bit there, is really really, really large and large enough to have these other elements. Now, if you want to translate that in a kind of a non-astronomical way, I'm sure all of you know the famous Conway games of life from the 70s. It was this biologist that started to invent the idea of evolutions and trying to replicate that into a computer. And there is something from the Conway game of life which is very profound, actually, if you look back to what they did. They found that many patterns that you would start with, and if you have never played with that game, just do it. It's very, very interesting, is you can predict what's going to happen because some are replicating, they are symmetric, and they don't go very far. But some of them, they evolve in an amazing way, and even in some cases could lead, depending on how you define it, to fractal element there. Now, what is amazing with that is practically, in general, I think I've never seen anything on that, you cannot predict what is going to happen. So there is kind of a predictable element, but also this unpredictable there. And I think, in a way, we are in this kind of regime when we're talking about life. Now, on the scale of the universe, the scale is just difficult to comprehend. I mean, if you take one atom's evolving chemistry, the chemistry evolution, keep it time scale and nanoseconds, you have 10 to the 26 chemical reaction for one atom or one structure, and you have about, depending on how you count that, 10 to the 80 atoms. So most of them are boring, the hydrogen and the ionized hydrogen, but still, even if you remove a 10-0 there, it gives you almost 10 to the 100. So a kind of challenge for Demis, I'm sure, to play with the beginning of the universe here. So this is what we're playing with. And with this in mind, of course, there is all this Drake's equation concept, statistics, because you can always try to bring statistics here. It's fine, but the numbers are so huge, it's essentially not really the way we think this true. But that's the two boundary conditions. So how far can we go deeper into that? And what the field is doing right now is trying to assemble these two boundary conditions to converge into something we can understand. And that's the whole idea I would like to defend now. So the starting point is we're clearly facing a lot of planets. So this is a very simple snapshot of 30 years of discovery of planetary system on other stars. Only very few parametric value here, mass of the star, the mass of the planet, the size of the planet, the radius in that case, expressed in Earth radius, and the period of the planet. Just to help you to read this, there is Jupiter, there is the Earth, and there is Venus. And this is two different techniques. I just don't want to go into detail here being used to do that. So there is clearly now a pattern that's emerging. The first one is we have to admit we fail to find a system like the solar system. Very few Jupiter like we have, and clearly none Earth and Venus-like exactly planet, while we found Venus size, Mars size, or mass, but most of them, they turn out to be in a short period. So it's been a shock to realize that the kind of concept we had for the solar system was not the concept in the universe. We seem to be a little bit aside this, not really what we found. It's also a gift for me because it turns out that right now we don't have the machinery to find a planet like solar system planets. So we're lucky, in a sense, that the universe has been kind with us, that producing so many planets that we can detect. Now, if you go a bit further and you ask yourself, how do we understand the gaps here? And the first one I would like to make sure with you, these lines are the kind of technology limit we are dealing with right now. We're working hard and we're going to move in through these gaps, but anything on the right side, there's no way we can find anything because it's too difficult. It's those ratios, structure of the stars, there's a lot of elements that makes our life difficult. It's not going to be like that forever. There is no boundary condition, you don't break the law of physics by going through that, but you still need to work hard. That makes a lot of incentive and good reason for the new generation of astrophysicists moving in that directions. But something which is fascinating, if you start doing a bit of statistical analysis of this data, it doesn't show up on this diagram because there's so much, biases and threshold there. But you get a very interesting numbers, which this kind of a group of planets that we call super-Earth and mini-Neptunes, and maybe we'll come back on some of the mini-Neptunes later, which are systems with a period of 1 day, 1 week, 2 weeks, and the size of maybe the Earth, a bit bigger, smaller than Neptune's, whatever you want to call them. They are the vast majority of the planet that you have on stars. So when you look at the stars tonight, think about that. So actually, most of these stars, especially the one look like the sun, they have systems like that. There is a bit of them that have planets like Jupiter, and there's very few with this extreme planet called the hot Jupiter there. So this is really what we're facing here. So it's a very interesting situation because essentially all of them, if you have them orbiting around stars, they're just too hot. So they are Some of them are lava planets, and way too hot. Well, the trick is some of them are not orbiting stars, like the sun. They're orbiting stars a bit cooler than the sun, which actually, luckily, is the majority of the star in the galaxy. So the more you go down in size and mass, the more you have in the galaxies. So there are some of them, and there is some extreme system like TRAPPIST, where you have a very compact short period system of a planet which is qualified as rocky based on the mass and the size you can measure, you can compute the density, and you find that it's kind of a mini-scale version of the solar system in terms of energy received from the star. So we can imagine that some of the planets have the same condition that the Earth. This defines a good planet to sustain life. This is what we usually define as habitable zone. But unfortunately, the story I'm telling you, we don't have evidence for that right now, but you will see that there is way to move forwards on this atmosphere of a planet. Now, what I would like to come back is, what is the reference here we're talking about? And I would like to kill some idea here. First, the Earth is not a static planet. It's a very dynamical system. And it's not only because we're there, and we talk a lot about Anthropocene, it's just through the story about the Earth. When you look at the story like a clock, here you start at 6 o'clock, you realize that the way the Earth have evolved is very complex, and at the end, you get what you get through the complete evolution. So it's not a fixed system. It doesn't only depend on when you make the planet, it's also how much stuff is falling on the planet. And just look at the moon, you realize that a lot of stuff has really impacted planet Earth, which is good because it happens to come from the far end of our solar system, which is full of carbons in a kind of format of icy carbon. So we had a lot of carbon. It was really raining carbon. So the carbon is all the CO2 we have. Most of them comes from that region there and really fall a lot and bring this carbon-heavy element that we have in the Earth. Of course, the atmosphere of the Earth is built up as a balance of what you have inside and the kind of pressure balance you have outside. And for some time, the Earth was essentially very close to Venus in a kind of structure, not with the same pressure, but certainly in a similar atmosphere, very different from what we have right now. And then we all know what happened, something a bit mysterious that we call it was a prebiotic moment. And then we started to have gradually transformation of the atmosphere. Now, that nice story I'm telling you here, it's just a story, actually, because we have no data, practically, from the first billion years of the evolution of the Earth, where everything is happening, because this first billion years is absolutely critical, because everything happened at that moment, and at that moment, after 1 billion years, life is there, fully functional, completely alive, already in most of the place of the planet. So the reason why we have nothing is because we are alive still now, because of plate tectonic recycling the CO2. At the same time, they kind of messed up everything and remove any traces of that moment. You have some element like zircons, but they don't tell you much of the story there. But most of the rocks, and I can tell you a lot of people would love detecting rocks for that time and trying to find out what it is, actually fall down and will recycle and mix up and re-emerge later on into the atmosphere. So this is where the astrophysics is great, because we have so many planets, and we can look at all of them, and we can compare with the Earth other systems. And that's the whole idea what we're trying to do. So practically, and we've seen already this spectra there, if you look at different stage here of the evolution of the time scale of the Earth, you end up with different spectra feature. And you don't need to go into great detail to see there is a massive difference here, because the dramatic evolution of the atmosphere is such that by looking at many planets, we already would get some kind of idea what's going on there. Now, of course, the mysterious moment you create life, it's still mysterious. And what the people do right now, they're trying to recreate that moment. Roughly speaking, and as a rule, and would deserve a whole workshop on that, there is 3 main mechanisms was mentioned. The most likely one, the most advanced these days, is what comes from the cyanosulfidic chemistry. HCN is kind of extremely like a spring energized molecules and can get down the whole chain of reaction you need to create the situation we have on life. There's also some element, remember, from the Miller and Urey experiment that could trigger some specific moment due to the energy you got in the massive impact. So there is a combination of what people are studying in the chemistry lab from when we study in the planet, but what we all agree, there is a link between the two, because planetology is the lab to create the chemistry of life on the planet. So you have to connect the two, and planetary science, potentially looking at many planets you find around other stars, give you this clue. Now, we all know the impact of life. It was mentioned many times. We know that about 2 billion years ago, there is a massive change into the amount of gas you have in the atmosphere. This is likelihood the production of life. But just pay attention that life was already well settled before that moment, where there were not much traces of impact on the atmosphere. So the fact that you detect an atmosphere which is different without the oxygen does not mean that you don't have life on the planet. And there's many other ways to look at this. Now, I would like to finish with this picture. It has been mentioned already a couple of times here. This is a famous one when you turn a spacecraft from far away in the solar system and look at the Earth. It's a blue dot from Carl Sagan. So the reason why I show that is this picture from the 90s actually may become a picture from the 2040-50 based on other planets, on other stars. The reason why we want to do that is not because we want to make a picture like that. Is when you have a picture, you can make a spectra. So in that case, this is a spectra in the infrared here, because it's where most of the energy comes from a planet like the Earth. So thermalized 12 micron here, and we need to go to space for that. But you can think that you can also observe that in different wavelengths with the next generation of machinery that we're building. And I want to mention this extraordinary equipment right now the astronomers are dreaming about, these 42-meter telescopes that's being built in Atacama Desert right now. This telescope have the capability, it was designed from the beginning, to be able to produce some kind of image like that on the nearby stars. And this is what the astronomers have right now in line. So stay tuned, and let's have another meeting, maybe specifically on some aspect of this meeting. Thank you very much.